post it. So I want to basically help you with your first program, which is going to be the lab tomorrow. Now, so let's just quickly take a look at the syllabus. So I'm going to share my screen, see what else is in chat. Okay, good. All right.
On the thingy, I was like,
Okay, it's recording now. Thanks for pointing that out. I wanted to make sure. I don't know why that. I don't know. Anyway, thanks. Okay,
yes, sir.
that was a good question to ask. Okay, so so when we do it, so for all the labs, we're going to use very, very similar boilerplate. And on the rare occasions where we're going to actually change the configuration words, I'll tell you about it. So you might as well go ahead and make an include file that has all that set up for you, and then you just have to include the file. So I'll show you how to do that. You don't have to do that if you just want to paste the words in every time you do it, that's fine. Okay, so let me demonstrate that both ways, and I'll do that in just a second. The configuration words. The configuration words go into program memory. And the some chips, and not all microprocessors do this, but a number do, and a lot of the PIC parts do. And what the configuration words do is they flash into the memory when you write in your program some basic features that set things up. Like for instance, whether you're going to use an external crystal for the clock, or whether you're going to use the internal clock module, whether you're going to use the phase lock loop to get to the highest frequencies, or whether you're going to leave that, allow that to be turned on or off in software, whether you're going to activate the watchdog timer, whether when you program a code in, you're going to build in code protect and data protect so people can't reverse engineer your code and stuff like that. If you put on code protect, then you can write, then your code's written to the chip. Somebody else can take that chip and they cannot read the code. They can erase it and reuse the chip for something else, but they can't, and they can run the chip with your code, but they cannot pull your code out into the integrated development environment and copy it and change it and rewrite it or whatever. And then there's some other things for brownout protection. If you're running it off a battery, when the battery runs down, what we don't want to have happen is that as the battery voltage drops below the lowest allowed operating voltage for the chip, then unpredictable execution could begin to occur in the software, which means that the chip could, let's say this, I mean, this is unrealistic, but let's say the chip was running on a battery, but it was controlling some big hydraulic arm. Well, you wouldn't want it to start doing weird things with the hydraulic arm. You want it to shut down gracefully as that battery voltage drops. And so brownout protection is that. You can pick a voltage level. Once the battery voltage drops below that level, it shuts the chip down. It doesn't let it just shut down, kind of in a haphazard way as the battery voltage gets lower and lower. Because again, what would happen is there's no guarantee it would gracefully shut down. It might very well start doing weird things. It might read in an instruction, but some of the bits might not get transmitted because the bus part, maybe a few lines on the bus didn't work right at that slightly, lower voltage than was legal. And so then you might get the wrong instruction, and that instruction might, execute some command that was, disastrous. So you don't want that. So you want graceful shutdown. So, but if you're not running it off batteries, it doesn't really matter. And there are a bunch of things. Okay, so we'll talk about the configuration words. We're going to kind of hit those light because I don't want to make that the focus. Then you have to define some variables. And in the assembly language, you pretty much have to define all your variables at the beginning. And you do those outside of your program. It's not like C where you can kind of define them on the fly. And then if you're going to use, there's 256 bytes of non-volatile electrical programmable read-only memory, not flash. It's separate from that. And it's not where the program's stored, it's in the data memory. And this allows you to save variables and then power down. And then when you power back up, you can retrieve those variables from the EEPROM. So they're non-volatile. But we're not going to use those today. In fact, we may not use them at all. And then if you're going to do an interrupter routine, which we are going to do later, but we're not going to do that today. So you would have to set these up. And then finally, you set up your basic code and any subroutines. Now, in assembly language, we call other things that we call subroutines. We don't call them functions. In C, we call them functions. They're very, very similar, just slightly different the way they're used and the way variables are passed and things like that. Okay, so this first program, we'll have a little. It's always good to identify every program you do. You know, put your name on it, the date you wrote it, what it's supposed to do. And if it's a real complicated program, then you want to probably put a lot more information, like how the data is stored, what things have to be connected and how they have to be connected to make it work correctly, just all that. And then the configuration words, the include file. We're going to set up an include file and put the configuration words in that, and then you can reuse that include file for every program you do, with maybe the one exception when we do the sleep study, because we will change one of the settings in the configuration words for that. So then we're going to define some variables in our main routine, and then we're going to set up the clock module in all of our registers. So we talked about our peripheral ports last time, and we talked about how the difference between the port and the latch and then the TRIS register, which is basically the data direction register, and then the analog select register. There's a couple others we're not going to worry with for pull-ups and for drive levels. We don't really need to use those. And remember, we have 3 ports on this chip: a port A, port B, and port C. Port A has 6 pins in it. Port B has 4, and port C has 8. And the port A pins, a bunch of those are tied up doing other things. 2 of them are tied up using the programmer debugger header. So A0 and A1 are tied up with that. A3 is the master clear, so it's tied up with that. And then we actually have RA5 and RA2 are tied up. They're already pre-connected to the RGB LEDs, 2 of the colors. In the B port, all 4 of those pins are available, although 2 of them are somewhat dedicated for use with I2C because they have resistors wired to them, but you can use them for other stuff if you don't want to use them for that. And the resistors won't affect it too much. And then finally, we have the C port, and most of those are available. We have a couple of them that are tied up to the header where we're going to talk to your laptop or desktop using a USB TTL level to UART dongle, and it plugs into 2 of those pins, but that's it. All right. So anyway, so we're going to use some of these pins. In this particular, because we're blinking the Hello World LED, we're going to deal with the 3 connections to the LED, and we might just use one initially. And those connections are the green, the blue, and the red. The green is RA5, and the blue is RA2, I believe, and then the red is RC6, is C6. So okay. And if you have any questions about that, you can always go and look at back here in the lab. And we have the pinouts for the Viva board right here. And it comes up on a Word file, and all the various things that are connected are in this file. And you can see, let's see, a little too much there. Okay, so, and here are the LEDs. Green is 5, blue is RA2, and RC6 is red. Okay, so if you ever have any questions about that. Okay, and so we can put this down. All right. So and then we'll actually, so we'll set up the clock module. We're going to make it run at 4 megahertz. It could run up all the way to 32 megahertz. but we're going to use it at 4. It's kind of a better value for analog to digital conversion, some other things, and also for PWM and whatnot. And then we're going to use, we're going to set the TRIS registers for ports. We really only need to set it for A, B, and C. We'll set that up, and then we'll set up the analog select lines and the latch. And so we'll talk about that. We always have to do this for every program we write. And then we'll actually do the code. And the way the code is going to work, we're going to turn on the LED. We're going to delay for about a second, or maybe a little less than a second. We're going to turn off the LED. Then we're going to delay again. And then we're going to loop and start this process over and just keep going. And then we have to write a little routine that we're going to call as a subroutine for our delay. And we'll call that routine delay. It's just convenient to do that because it has a few instructions in it. So it's easier to write it once here and then call it 2 times in our actual loop. Okay. So I'm gonna add, so this is what I'm gonna put in. I'm actually going to, we always want to include this file, and it's called p16f1829.inc. Now, if you've loaded up the IDE on your computer, you've got this file in the libraries, and you can find it. It takes a little looking to track it down. And what this has in it, it defines, it creates names for all of the absolute addresses for all of the special function registers in the processor. And that's super helpful. It allows you to use names instead of having to go back and use numbers for addresses or give them names yourself. This does a lot of work for you. And so that's how we can write we can write pin names, and it'll recognize all that because that information is in this file, and we're going to include it in our program. I also like to put in this one. I think you could, strictly speaking, not bother, but it's called a list directive. And what it does, it tells the IDE actually already knows what chip you're using because you specify that when you set up your program. But this tells, I don't know, not sure why this is in there, but anyway, it seems like a good idea. Processor is the 16F1829, and then R stands for radix, and it equals decimal. This means that if you just write a number, it's considered decimal. So again, if you want to specify an octal number, if you want to specify a hex number, then for hex we do we write that as we write 0x, and then 0x, and then the little numbers, whatever it is, and usually only 2 because that's 8 bits. And if you want to do a binary, then what we do is we write 0 lowercase b, and then usually 8. Usually you put all 8 digits in. I think I only got 6 or 7. All right. So, but if you just want to write a decimal number, then you can just write it. Okay, and you want to get this set up for your standard program so you can include this in each one of your programs automatically, and I'll show you how to do that. Okay, here's the configuration word when it gets all written out, but it's easier actually to go through this in the IDE. So if we look at the IDE and you click, you've got a bunch of windows down here at the bottom, variables and a bunch of stuff, and we'll go back to those. You're seeing more here because I added some when we did this the other day. If I click on configuration bits, then I'm going to set this up. Internal oscillator. So you can pick a bunch of stuff, but that's what I want. We want the watchdog timer off because that'll really screw everything up if you turn it on. The power up timer enable. Master clear pin must be set to on. Code protect off. Code protect data off. Brownout, you can leave it off. We're not running off the battery. Or if you are running it off the battery, you can put that on. It doesn't really matter. So put it on if you want. And then clock out enable. Internal, external clock switchover off. We're using just the internal clock. Failsafe clock monitor off. We're using an internal clock. And then flash memory self-write protection. We'll turn that off. Phase lock loop enable off. Stack Overflow, underflow, reset. We'll leave that on, doesn't really matter, it can be off. Brownout voltage, you can take low or high, whatever. And finally, low voltage programming must be on. If you turn this off, you can program it off with your snap. But once you program it off, you'll have to bring your board in and we'll have to program it back on with a PIC-Kit3 or an ICD4 or an ICD3 or, you know, one of the other slightly more expensive programmers, PIC-Kit4, PIC-Kit2. Anyway, so we do have to turn, once you get all these selected, then you just hit generate code and it turns it in to this code right here, which you can copy and then you can paste into your routine. All right, I think I've been through this before, but let me just so you just see this. Let's just do this one more time. So let's create a new program, file, new project, and the guide walks you through all this. And so microchip embedded, standalone. Select those two things, hit next, type in PIC 16F 1829, and then you see it turns it into all caps automatically, no matter what you actually type. So that's good. Hit next. We're not going to use a header. And then I'm using the ICD4 programmer, so I'll select that. You're going to be using the snap, so you would select the snap. If your snap's plugged in, you should see a serial number associated with it. And if you don't see that, it means there's something wrong. And one of the students emailed me and had that situation. So the first thing to check is make sure you're running the IDE version MPLAB X. Remember, there was a whole bunch of just MPLABs first. So make sure it says MPLAB X IDE version 5.25, and that's the version you want. If you run a much earlier version, put out maybe a year and a half ago, we didn't have snaps then. So you may, or maybe 2 years ago, there were no snaps. So there will not be an option for snap. All right, so I'm going to select my ICD4 and you can click on the serial number if you want. And then you're going to click on MPASM. If you loaded up version 5.40 or later, you're not going to have this option. That's why we're using 5.25, because they took this away, even though it's still there, has to be, because the compiler compiles it to assembler, and then it has to be assembled to machine to be loaded. So we know the MPASM is still there. I believe you can get to it, but I spent some time trying to figure it out. It's too complicated. I threw up my hands and said, okay, forget it. We're just going to stick with this one. You can switch, once we switch to C, you can switch to the later one if you want. That's fine. All right, and then you give your projects a name. And this one, I'm just going to give it some stupid name and then you just go finish. And then boom, here it is. Now, if you click on it, you'll see that it should say unset as main, which means it's set as main. All right, and then we're going to go down. We're going to look at two things. One, we're going to add a source file. So we expand that, but there's nothing under it. So we highlight it, right click on it, hit new. We go over here and we do pic _ 8-bit _ simple.asm. And that gives us some simple assembly language. You give it a name, and here's what you're going to see. Okay. And if you want, then you can just take these configuration bits, copy them right here, and you can go up here and you can erase this and put that stuff in there. And then you can also go up here and you can put another semicolon here, and you can type in your name or whatever, the date you're doing this or whatever. All right. What I'm recommending you do instead is put this in, go ahead and first under header, you can expand that, but there's nothing there, right? So highlight header, right click on header, and here you go, new other, and then assembler, and then assembly file.inc, which is the include file. We call them headers in C, but in assembly, we call them include files. Same thing, just different name. In this one, I'm going to give it a specific name, config. It's going to be config.inh. I'm going to finish it. Then here it is. It's totally blank. And what I'm going to do, instead of copying this into my main program, I'm going to copy this into my header here, like that. And I'm gonna put in that list directive that you saw. I think right here, list, and then that was, and let me make sure I get it right because I don't want to, let's see, it's here. Oh, it's here. All right, here. Yeah, so these two things here are this one line. You don't even have to do this if you don't want to. It's not that big a deal. And so then I'll just put this in here. All right, and now once you get this done, you've got that in this config file right here that you just made down here, and so and I think that's it. Yeah, that's it right there. You can also go find where this is in your directory and copy this file, and then anytime you want, you can just create a new config file. It's probably better to go ahead and create the file like I just did and paste this in. So you can save this in a notebook or something or a Word document and just paste it in whenever you need it. And each time you can create your config.inc. And then in your main file down here, where we click on this, let's see, and where I put this in, instead of doing that, what we'll do is we'll type in here, type in config.include, and then we don't need any of this because now we've got it in our config file. All right, so I'm just gonna get rid of this. Let's see, delete, I hope. Delete. Yes. Okay, so that goes. All right, and then now I want to make sure this is set as main project. Okay, so now this is set as main. Okay, now let me just make sure. Here's my and I'm gonna get rid of all this stuff up here. Discard. Okay, and then I'll get rid of all these, and then I'm gonna bringing them back. I just want to double click. Should be back and double click. So now here's my code. So here's my config file here. And sorry, here's my config file here. So this has everything I need. Now I just have to put. Now I'm just going to put in here. I'll put in my name. Okay, and then down here, I'll put in the include file. Now, for the most part, you don't want to put things in the first column except stuff like this, labels and compiler directives. Okay, and once you get this, then now each time you do it, all you have to do is copy your config file in and then do this. And what it does, it kind of declutters your program a little bit. But if you want to paste it in there, that's fine. You don't have to do this. I just thought I'd throw this out. Okay, the next thing that's available here is called your reset vector. Whenever you start the program, it automatically starts executing program instructions stored at program memory location 0000. And we're going to put a go to instruction and we're going to say go to start. And the reason we do that is because at location 3, then we are, yeah, I think it's location 3. We put our interrupt file if we're going to use an interrupt. And so that's where, so on power up, control is transferred to location 0, and on interrupt, a location is transferred, execution is transferred to location. I think it's 2. I always forget. I'll double check that, but whatever. We'll show you that when we get around to it. So this go to start would jump us over our interrupt routine if we had one, and then we have main program code, And this allows the linker to put our main program wherever it wants. This would be useful if we're going to make it a relocatable code. You can make it absolute code by using the org directive. You can make it relocatable by using the code directive. And we'll use the code directive both here and here. But here we specify the value of 0 because that is the vector. It has to be there. Whereas where start is now, since we're branching to start, the compiler can put start wherever it wants, and then it'll put the address here for the go-to, so it'll automatically branch to wherever this gets put. Okay, and then in this one we had go-to $. The $sign refers to your present location. So if you wanted to branch forward a few, you could $+ or $sign minus, or you could just say go to start, which would be the same thing actually in this case. The label start is, since there's nothing between the label and this instruction, it's effectively the same location. And then we have an end compiler directive end. So we're going to replace this go-to with our actual code. All right, so now we're ready to do our setup stuff. And so if we remember the setup stuff, so what we're going to do in that, we're going to set up our clock module and our tris and our AND cell and our latch and our port stuff. So let's do that. So there's the configuration. Now, we're going to define our variables first. I skipped over that. We're going to define our variables. We haven't done that, and we're going to need a couple of variables for our delay routine. So let's set those up. There's a whole bunch of ways to define variables. You can use the #define, you can use db, you can use data, you can use C block, and N block or NC block, NC here, and you can use equate and fill and DA and D. There's a whole bunch of things you can do. So I suggest you either use the equate or the C block instruction. And we'll do the C block. So here's the C block. You say C block and then you write the beginning address. Now, if you remember, when we did our when we looked at the data sheet and we looked at memory, you'll remember, let's see, memory organization. So if we go down to where we see our data memory pages, not our program memory, our data memory, we have 31 banks of data memory. In bank 0, you see we start at 0. We have the core registers. We start at F, we start at C, and we have port A, port B, port C, skip 2. And then we have these, and basically, and then starting at 20, we have our general purpose registers. So we could do our C block there. We could do our C block up here in the common RAM at 70 hex. And then we wouldn't have to use bank cells, but I'm going to put it at 20. So we could also put it over here at A0, 120, 1A0, 220, 2A0, 320, 3A0, and so forth. Those are all valid all the way up to bank 12, where we could put it at 620, but we'd only get 48 bytes. Well, we only need 2 bytes, so we could put it anywhere we want it. Okay, so that's how you know where you can put it. And so then let's go back to here. All right, so I put 30, but we could just as easily make that a 20. It's really no big deal either way. So we'll just make that a 20. Okay, now, so I defined the C block to start at location 20, which is the very first bank of RAM in our bank 0. And we're going to write variable A, variable B, and NC. In this case, these will each be 1 byte. And then that's NC block there. So we're done with it. And oh, did it change back to, it did change. Look, it changes back to 30 when I click off. That was crazy. Well, it's really not 30 anymore. That's a bizarre behavior. All right. So anyway, and then if you want to go look at all the directives, there's a little PDF you can do. We'll talk about some more of them. There'll be a whole bunch we'll never use. we're just going to use a few of them. Okay. So now we're going to write some code. Now, I wrote a little bit different code routine here. So I think I'm not going to do this because this is going to confuse you. So what I'm going to do instead is switch out of the, let's see, I think I actually have a different routine. Yeah, here we go. Okay. So first we're going to set everything up. And so the first thing we want to do is set our clock for 4 megahertz internal clock. Okay. So we started with this, we got this far the other day. I'm gonna use my bank select instruction to set the bank register for the proper bank with OSCON. And then I'm gonna move local, or literal rather, move literal to W. And I'm gonna put in hex notation 6 alpha. Then I'm gonna move the contents of W to F, and it's gonna get stored in OSCON. That's gonna set the oscillator control register for 4 megahertz using the internal clock. We're going to use the internal clock because we specified it in our configuration word, and we're also programming it in the control register. Some of the things in the control register will override the configuration words, and some of the things in the configuration words will override the control register. So you kind of got to, it's a little bit tricky. Now we're going to bank cell tris A and clear it to make all tris an output. Then we're going to bank cell port A, and we're going to clear that. And that's going to set up our port A. Now, the tris registers are all inputs by default, and the outputs, but the actual ports could be anything. And we really also ought to do the latch here. And because when I wrote this code, we didn't have an RGB LED, we just had a single LED. I didn't have to worry about the other 2 colors being on, and also because we have a common anode. If we set port A to 0, we will turn on both the green and the blue LEDs. So we really don't want that. So we're going to change that a little bit. We're going to load a value in and write that out, or maybe we'll even use some bit set and bit clear instructions. Okay, and then once we get done with this setup, then we're going to do the blink loop, and all the blink loop. Then we're going to bank cell the latch A. We're going to set bit 5. We're going to call our delay routine. We're going to reset the bank cell to latch A, clear bit 5, call delay again, and then go to blink loop, go back up here and do it all, and we'll just loop all the way through this. And then all we have to do then is understand our delay routine. So let's look at that real quickly, and then we'll just write it all and make it work. Here's the delay routine, and this is copied out of the guide for your lab. So this is exactly what we want you to do. So you don't need these numbers over to the side. So we want to have a label delay, which tells us the start of this delay routine. And then we have 3 other labels. We have a label called outside, a label called go on, and a label called inside. And what these do, these allow us to do a 16-bit count. If we just did an 8-bit count, we could do it with a lot fewer instructions, but we want to do a whole 16-bit count. And we want to use variable A and variable B. We want to use variable A as our, I guess we're using variable A as our higher order variable, and we're using variable B as a low order. So if we looked at this, we would see, let's see, turn on the light here. So we would see we'd basically see variable A and variable B set up sort of like this. So this is our high order and this is our low order. And what we're going to do, we're going to write FF into here and FF into here. And the first thing we're going to do is we're going to decrement this one by 1 to give us FE. We'll check to see if it's 0. If it's not 0, then we're going to decrement this once to FE. check to see if it's 0. If it's not 0, we'll decrement again to FD. Check again, it's not 0, we'll decrement it again to FC. And we're going to go all the way down to where it's finally 0, 1, and then we'll decrement it one more time, and it'll be 0, 0. And when we get that, then our instruction that we're using is called the decrement F skip. Let's see, it's DEC F skip on 0. So this decrement F skip on 0 instruction is gonna make it really nice for us. So we'll see how that works. But that's the idea. We're going to decrement, and then once this happens, we're going to go back here, decrement this one time to FD, and then we'll reset this to FF and do this all over. So we're going to do this. We're going to do this loop essentially 256 times to go from FF to 0, and then we're going to decrement this. So in the end, we're going to decrement this 256 times 256 times, and that's going to give us 65,000 something. It's about 65,000. And that's going to take the processor about 3/4 of a second to do. And so because of that, that's going to give us a nice little delay. Okay, so that's how we're going to get our delay. Okay, so let's look at this. So I'm gonna, let's see, I guess we're back here. So that's what this routine is going to do. So how's it going to do it? Well, so first it's going to bank cell variable A and store FF into W and put W into variable A. And then it's going to decrement variable A. And this instruction, decrement F, skip on 0. So it's going to decrement variable A. If it's 0, it's going to skip, and that's going to return back to your main routine. But it's not going to be 0. It's only going to be FE. So then it's going to go on. Goes down here to go on, and it's going to move FF into variable B, and then it's going to decrement variable B. And if it's 0, it's going to go back here and do it again. And it's going to go in a tight little loop here until it decrements it 256 times. And finally, it'll be 0. And when it's 0, it'll decrement it that last time from 1 to 0. And it'll skip this instruction, this go to, and instead it'll go to outside. Goes back up here to outside, decrements variable A one more time. It's still not 0. So it does not skip. It goes to go on, comes down here, that reloads variable B with FF, does it another 255 times, goes back, decrements this once more. And so we're decrementing variable B of 256 times each time we decrement variable A 1. And we have to decrement variable A 256 times as well before we finally get it down to 0. And now we skip this go on and we hit return back to your main routine. So that's how this, you can do this a whole bunch of different ways. This is just how it's set up. Okay, so here's another time delay routine. You can look at it if you want. And this has an extra wrapper around it that lets you execute the delay routine, in this case, 2 times. It gives us something closer to a second, and we change the number instead of FF. Anyway, we change it. Well, this is a little confusing, which is why we switched this. Okay, so I'm just gonna, let's see, sorry. I'm gonna copy this because it's gonna make it easier for me to do this. I think I'm gonna copy it. Maybe, oh no, you know what? I made a picture. I want to be okay. All right, so I'm gonna skip out of this now, and then I'm gonna start writing in my routine. Okay, so here's my code. So here's my main routine. Now, so all I have to do here is start, and I have to put all my code in here, starting at start. So the first thing I'm going to do is the little boilerplate stuff. And I think I have, let's see, let me pull up let's see, here, I think. Yeah, not that one. So my little big lamp. Oh, this is what I want here. No, sorry. Here. Yeah. So, so, so we'll go down here. We've talked about most of this, and you do need to read through this. Okay. So let me go all the way down. So this is where it begins to tell you what to do. And okay, so I kind of set this stuff out. And I changed a little bit. So you can follow this exactly, or you can create the little header I created, whichever one you want to do. All right, so we're going to create our variables with the C block instruction. So I'm just going to do that. We'll shrink this down and we'll put these up here after the include file. Okay, variable A, variable B. These can be on. Probably better to put them on separate lines. All right, then I'm going to go back here. Let's see, it is in here. Now we're going to go down, and we've already got all this set up. I'm gonna set up my oscillator. It may pick up this other stuff. If it does, I'll just delete it. Okay, and then back to here. So now this is after start. So now now what I want to do here, I got to get rid of these numbers. Now, one point I do want to make: when you write assembler code, the only thing you want in the first position are labels when you're writing your code. So move your bank cell and your two instructions off of the first column. Don't put them in the first column. All right. So now that sets up my oscillator. Now I'm going to do a couple of things. I'm going to set up the TRIS register. So I'm going to set up TRISA. I'm going to set TRIS A. Well, I'm going to have to bank cell it first. Bank cell TRIS A. So we're going to do that. And then we're going to move literal up to W. And what I'm going to do, I know that I want pin 5 to be a 1. So maybe what I'll do, instead of doing this, maybe I'm just going to do bit clear F. This is another instruction, and I haven't talked about this one yet, so I'll explain it right now. So I'm going to, this one requires two fields. It requires the register you're going to deal with, which is in this case TRIS. Now, this only puts the lower 7 bits in this instruction because the upper 5 bits were put in the bank select register with the bank cell instruction, giving the 12 bits. All right, so here's my bit clear F, there's TRIS A, and then I have a second operand, and I put a comma. Well, I can put a comma right there, comma, and now I put a number 0, 1, 2, 3, 4, 5, 6, or 7 to specify which one of the 8 bits in the TRIS register I'm going to affect. Now, TRIS A only has 6 usable bits. The bit 7 and 6 are not used. So I could change those. I wouldn't do anything. But I want to make bit 5 a 0. So that's why I'm going to clear it, because by default it's a 1. So I'm going to put a 5 here. So that's going to take bit 5 in the data direction register for port A, the TRIS register. It really stands for tri-state because we use tri-state buffers, remember? And they connect the flip-flop to the pin. So my tri-state buffer for pin 5, I'm going to clear it, which means I'm going to turn it on because it's active low. And I'm going to connect the flip-flop to the pin, making it effectively an output. Okay, so that might have been confusing, but this is how we make an output. We clear the bit in the TRIS register. If we leave it set, because it is set by default, then it would be an input because the flip-flop would not be connected to the pin. All right, so that's going to take care of that. And then I don't really have to mess with the AND cell bit, but I'm going to do it anyway, just because it's good programming. And the reason for that is, first off, it's an output. So you can actually Ignore the AND cell bits on outputs, although you're not supposed to. You're supposed to set them for digital if you're going to use them for digital. And because it might increase the current draw a little bit if you don't. But we'll do that. So ANSELA, AND cell A, so bank cell AND cell A. And then I'm just gonna clear F, CLRF, AND cell. I'm going to clear it. So I'm going to clear all the bits in the analog select register all at one time with the clearF instruction. I could also do a move L to W 0, 0, and then move W to AND cell A. That would work too, but this is a little faster. All right. And then I'm going to go ahead and I'm going to bit set F. Oh, well, I have to do the latch A. So I'm going to do LATA. Well, I'm going to do bank cell BANKSEL LATA. And then I'm going to bit set F LATA, comma 5.
Dr. Morton?
Yep.
Sorry to interrupt, but I believe on line 23, you have an error with the bank cell. You have it written as bank cell.
Oh, yeah, you're right.
Sorry about that.
No, that's okay. Oops, I better put it down. Yeah, thanks. It would have, I think it would have flagged that eventually. All right. Okay, so now this sets that bit. And the reason I did that, you don't really have to, but that starts with the LED off, which I kind of want to do. All right, now I've got pretty much everything I have to get set up. And since I only made bit 5 an output, I shouldn't have to worry about any of the other LEDs being on, but that might happen, we'll see. All right, now I'm gonna go down here and this is gonna be my loop and I'll just call it loop. You can call it, I think in the other routine, we called it, go down here. I think we called it, let's see, what did we call it? Well, this is my delay routine. So let me set up my delay routine and then we'll go back and we'll fix the rest of the stuff. So now I'm just gonna paste this in. And so I'm going to do this down here. And let's see what happens if we do this. Okay, now I'm going to have to fix this up. Again, remember we only want the labels in column 1. So I'm going to space all this stuff in. Outside, delay is a label, outside is a label. And then some places I picked up the numbers when I copied it. You don't want that either. Go on as a label, but move LW is not a label. Move WF is not a label. And then inside is a label. And decrement is a label. And go to inside is a label, is not a label, and go to outside is not a label. Okay, and then this can be backed up a little bit. That's fine. All right. So now,
excuse me, Professor.
Yeah.
Earlier you had used clearF, and then another time you used BSF.
Right. So
or BCF. Well, what's the difference?
So clearF clears all 8 bits all at once. Bit clearF only clears bit 5.
Oh,
so
right. Okay.
BCF stands for bit clearF, and then clearF is just clear the file register. And BSF is bit setF, only sets bit 5.
Okay, right. Okay. Thank you.
All right. And then now, so now I have my delay routine and my loop. So now all I have to do is write the rest of the code. And so what I'm going to do, I'm going to use the bit set and bit clear instructions. So to turn remember to turn the green LED on, I want pin A5, RA5. I want that as an output, and I want to set it to 0 because it'll ground the cathode on the green LED and the RGB LED, and the anode is the common anode connected to power. So that should turn it on. All right, so I'm just gonna go ahead and do that. I'm gonna do bit clear F. Well, first I have to bank cell. And then I'm gonna do bank cell LATA. And then I'm gonna do bit clear F, LATA, comma 5. So this one does have a second operand. And then I'm going to do call delay. Call delay. Now, this is essentially in assembly, this is how you call a subroutine or a function. And we call them subroutines in assembly. So call delay is going to transfer control down here to delay. It's going to run through this 65,000 times, and eventually it's going to return. But somehow that didn't get, somehow it got dropped out. So we have to have a return there. Yeah, I don't know. That's interesting. How did that get left out? Is that not there? Oh, somehow it didn't get copied. I don't know. All right, anyway. And you can use uppercase and lowercase for all this stuff. All right. All right, so now, so this is my, yeah, I'm glad I saw it. So this is my delay routine here, and it's a subroutine, and we're defining that outside of the main routine, essentially. And here's my blink, my loop. So the first thing I'm going to do is bank cell latch A, clear bit 5, that should turn on the green LED, call delay. And then when I come back from delay, I'll execute the next instruction. And I'm just going to bank cell latch A again and do this again. So I'm just going to do this. And instead of clearing F, I'm going to set F. And then I'm going to call delay again. And then I'm going to go to loop A. Now with that, I should have everything I need. And with any luck, that'll work. So the first thing we do is we'll go ahead and compile it and see if it compiles. See if we get any errors or any problems. Okay, so we do have some error. Let's see. Oh, it couldn't find my config.h file. Oh, config.h. I mixed assembly language and C languages. Let's do it again. Okay, still had a problem. Found directive in column 1. Okay, so it doesn't like even the directives in column 1. So maybe I should space that in. Space this all in. Okay, let's try that. It's kind of finicky about column 1. All right, so list. Oh, it didn't like that. Oh, I see, in the include file. Okay. In the config file. So I'm going to move list out. I think it's okay with the include there. Okay, and down. All right, let's do it one more time. Okay, symbol not previously defined. I misspelled OSCON apparently. So OSC. Oh, I see. Oh. Where did I say OSO? Oh, I see. All right. So much for my spelling. And then symbol not pre MOVWF. Let's see. Oh, that's not right. Okay, I'm confused now. Okay. Why did it not like that? MOVWF. I see. It doesn't like that. Well, let's go back and look at. I'm sure that's the right thing, but MOVWF. MOVWF. Well, I'm not sure what's up with that. So okay. MOVWF. I don't know why it's got a problem with that. Oh, I don't know. Error.
It's not case sensitive, is it?
No, it shouldn't be. Yeah, it should not be.
Is there a difference between like using like a space and a tab?
No, I don't know. I'll change case just to make it happy, but I usually put them in lowercase, kind of my thing anyway. There must be a non-printing character or something. I don't know. There's something screwy here. Let's see what happens with that. My God. All right. Well, let me make it capital. It should be fine. Can't believe that.
Isn't it saying it should be on line 41?
Oh, maybe it does. Yeah, it does say line 41. So maybe we did do something wrong. Oh, I see. Can't have that. Okay. Yeah, you're right. Thanks. Okay. Yeah, I didn't read it. And that's why you have to read carefully. All right. Believe it or not, I think we got no errors now. All right. Well, so we had a few glitches. I probably should have just, if you type it in ahead of time, you can get it right. But all right. Okay. But I didn't want to do that. I wanted you guys to see me struggle through it, just like you will tomorrow. Okay. So now it assembled. We got build successful. So now we can program the chip. Okay. So let's look at that. So and then I'll talk a lot more eventually about all the things, but okay, so here's my ICD4 and here's the little board. So we got the programmer plugged in here. I have power here, a little 5 volts input. And so we can shrink this down a little bit. Let's see. And hopefully we will be able to we'll program it. So now, so it usually wants to know what programmer you're going to use. And then it goes through all this. It's going to build it again, connecting to programmer. A lot of times, the first time you use the programmer, it always gives you this message. You can turn this off. I don't recommend you turn it off, but I think 99% of students do. But I kind of like to see it because it reminds me that it tells me it's doing what it's supposed to. And it's just a check to make sure it's gonna work. And then sometimes the first time you program it, it goes down and it loads. It has to load the firmware into your Snap programmer. Same for the ICD4 for that matter. But and then Yeah, see, updating firmware for the application. So it's screwing around with it. And sometimes it even times out when it does that. If you've got a slow connection, you might have to do it a couple times. But eventually it should work. Sometimes it takes a little bit. Okay, now once you get to this, erasing following areas will be programmed, program verified. You know that it's talking to your chip when it says target voltage detected, target device found, and device ID. Your target device found should always be the PIC16F1829, and the target ID, it has a built-in ID, and it's hex 4. So if you should always see that. Okay, so now it should be working. And look, the green light is flashing. Now, what I'm going to do is I'm going to do this again, only now I'm going to change and I'm going to build it for debugging main project. And then I'm going to program device for debugging main project. Notice you also have program device for production for main project and erase device. You may not get that selection. I don't know if the snap will do that, but my programmer will program it with several different voltages and make sure it's going to work with a range of voltage. So it's a more of a robust program. And then we'll program it for debug here, and then we're going to run the debugger. And I want to show you how that works. Okay, and it's almost done. So if you're going to use the debugger, you actually have to specifically program it for debug. And that's because there's some instructions included that are not included when you don't program it for debug. So it just saves a little space. And it's not very many instructions, but it's a little bit to give you the debug features. So they take them away if you're not going to use them. And then I go here, and this is launch debugger main project. Now that's how I do it. I think you can actually debug, and it's resetting. Okay, and now once it's all resetting, hopefully it'll be all set. And then you have some controls. Some of your controls may be hidden because you don't have enough room up here. Well, okay. It's taking its own sweet time to do this for some reason. All right, I'm gonna, I don't know why I did that. It's faulty. Okay, had troubles. So I'm gonna do this one more time. Maybe I'll just debug main project. I'll do this. For some reason, it's always been a little squirrely. All right, now in this case, it left it running. There is a setting. If you wanted to go into reset, you can set that up, but I'm gonna click the pause button there, and then I'm gonna click the blue reset button here. Now, this green bar, so this is what we call source level debugging. So I can actually follow the debugger in my software. And I'm starting here at go to start. That's where the reset vector, that's location 0000 in program memory. And the first instruction it's going to execute is go to start. So it's going to go up here. And then the next instruction is, it's not really a bank cell. What this next instruction is, if you look at it, it's going to be an MOVLB instruction. All right. So anyway, so I can single step through this. So I can hit this arrow here, which is step over, and I can hit this, which is step in. And I want to step over things that are going to take a long time, like my delay routine. So I'm going to punch this. I'm going to go to the bank cell. And then if we look at our variable memory, you can pull these up. You go to Window, Target Memory Views, and then I hit Special Function Registers. And I already did that the other day. And so here they are. Well, actually, I don't see them, so I'm going to hit it. So here are my special function registers. Now, I have, there is a W register. So let's see where a W register. So here's the BSR right there. Okay. What does the BSR have in it now? It's got 00000. I forget. I think OSCON. If we go all the way up here, memory organization, we just go back down here and look at our memories. We'll see where OSCON actually is because I don't remember. Okay, OSCON is in bank 1. So we're currently set for bank 0 because here's our BSR and it's got 0 in it. You get it in hex, you get it in decimal, you get it in binary. And then you get the ASCII character, which is, I guess, something for zeros. I guess it's a period. I don't know. Anyway, so I can change these, but I'm gonna step the next instruction, click on the arrow. And now that should have put 1 in the BSR, and it did. So now my BSR is pointing to bank 1 where OSCON is located because it's smart enough to know. And see. Yeah, and then this is, yeah, okay, well, anyway. Okay, so now I'm going to put 6 alpha into the W register. So notice the W register here, it currently has 16 decimal in it, or 10 hex, or 0010000. So if I step, boom, it's going to put 6 alpha in there. And now I'm going to move that 6 alpha into the OSCON. So I'm going to scroll up to the OSCON because I know it's in bank 1. Should be somewhere in here. There's OSCON. Right now it's got 38 in it. And it's probably going to still have that actually. And let's see. Nope, it's got 6 alpha. All right, so that's what it's supposed to have. Now I'm going to bank the TRIS register, which is right here. TRIS A currently has 3F in it. It does boot up all set as inputs. And remember, the A port only has six pins. 7 and 6 are not implemented, just 5, 4, 3, 2, 1, and 0. And I'm gonna bank cell it, and I'm gonna clear pin 5. So we're gonna bank cell. That's changes the BSR, and now I'm gonna clear the pin. And you see, boom, pin 5 is now 0. Now, if I want, I could also change this and make one of these other ones 0. And if you notice, if we look at the chip, notice now the green light's on. And the green light's on is because my latch, if I go to the latch A, which is somewhere here. Let's see, no, I've already missed it. I guess it was, I didn't see it. So the port, you can say port A is set to all zeros. So RA5 is putting out a 0, that's going to turn on the green light. Now, if I change the TRIS register for bit 2 here, so that's 0, 1, 2. If I change this, and I should be able to do this to I'll change this from 1F. If I change it to 1, let's see, I want it to be 1011. So that's going to be B. So if I change it to 1B, 1 or 0x 0x 1B. Oops, B. And then I hit carriage return. Now notice, now I've also turned on the blue LED. I've turned on the blue and the green. It's hard to see, but it's no longer just the green. And if I change this back to 1F, 0x1F or F, then I'll have just the green on. So you can see I can change these variables on the fly. And that's, so notice I'm turning the green and the blue on and off by changing it from an input, a pin, or changing it from an input to an output, or from an output back to an input. Now notice if I go down here to the latch command and I change this, right now it's 1, 0. If I change this to, so that is, that leaves my bit 5 as a 0. If I change that to 0x30, so 0x30, notice that I will change it off. Let's see. How come it didn't? Let's try that again. 0x30. I think I hit the wrong thing. Is what happened. No, let's see. Oh, I see it. I didn't put it in. Okay, now it turned it off. Yeah, and now you can see it. Now it put a 1 in the 5 position. And remember, if RA5 is a 0, it turns on the green LED. But if RA5 is a 1, it turns it off. So if I want to go back here, I just change this to 0x10 again. And when I hit that, boom, the green light's back on. So I can change any location. I can also look at my memory, program memory. I pull that up in the same way. I do the memory view. I go down to the target memory values and I go to program memory, and I did that. So here it is. Notice I can see at 0, I have a go to 0x3. And then at 3, I have start, or rather, well, yeah, it's location 3, line 4. I have a start, MOVLB to 1. Remember, that is actually our compiler directive, bank cell OSCON. Remember, I told you what the bank cell does. It creates an MOV LB instruction. And since OSCON's in bank 1, it's an MOV LB 0x1 instruction. And then I'm going to MOV 6 alpha, and I'm going to put that. Now notice this is kind of interesting, right? It says MOV WF into timer 1 gate control register. The problem is that that it doesn't know that I've bank celled for TRIS A. So the bank register is going to actually point me to TRIS A, but in bank 1 or bank 0 or whatever it is, I guess that's bank 0, that would be timer 1 gate control. And so that's why it gets it wrong. So it's not entirely, you can see it's timer 1 gate control, but I'm actually pointing to the TRIS register, which is here. So what it really is the OSCON register. It just doesn't know it. So you can see there are some limitations to the debugger. You have to be smarter than the machine. But this at least will give you a rough idea of what's going on. This is what's called a disassembly, and it also doesn't know anything about your variable names. So when I have like delay routine, notice here it's moving it into location 30. Doesn't tell me that it's variable A. It just says it's location 30, and so you have to know that location 30 really stands for variable A. And yeah, all right. So I think that's it. I'm going to stop there and give you guys a chance to ask questions if you want. We're about 3 minutes over. So,
Yes, sir. I was trying to download that software, but I have a Mac, and the only thing that it gave me was the one at the very top, and it was saying it's running off of the 5.4 software. So is there somewhere I have to go specifically in order to get the version of 5.35 or 5.25?
Yeah, you click, so back in the back in the here, we have microchip, MPLAB X, IDE, and XC8 archive. Just
I
click
can't
on-
see on your screen,
Oh,
unfortunately.
sorry.
No, you're good.
Yeah, here, let me switch back. You click on this. And it brings you to here.
I think it didn't move over again.
Oh, sorry, I didn't click, I didn't, okay. One more time.
Yeah, all right.
Here's in the lab folder.
Yeah, because I went to the micro, there you go. I went to there, but on the very top, it gave me that option for download for Mac OS patch.
Don't do, yeah, I don't know, that's got to do with this Catalina thing. I don't know, I don't know about that. That's confusing. The Macs are just, there's just a problem. But anyway, here are the various versions. So here are the MPLAB X IDE archives, and there's all these pages, right?
Yeah.
So what you want to do, the Mac OS, so you want to go back. So I don't know, let's see.
So, like I could do 3, 5 and just do the 5.35 MP
Yeah,
lab.
I think this is the one you could do right there.
Okay. I just want to double check.
Yeah.
Yes, sir. Thank you.
And whether or not you'll need to, you may need the patch for that.
Okay. Oh, if I got to do it, I'll cross that bridge when I get to it.
Yeah, I think you do. It says the latest versions of Mac OS 10.15 Catalina remove support for 32-bit applications. This means that current versions of MPLAB X IDE up to 5.40 will not run on this operating system without a patch. All current versions of MPLAB XC compilers are now compatible. Yeah, okay.
All right.
And then to get the right XC compatible, you go down here to, I don't know, is this XC? No, I guess this was it. No, language tools, XC8, yeah. So here you have, it's Windows OS X, Linux, Windows OS X, Linux, so forth. And just what I recommend you do there is, I like you to do 1.45. So
1.45. Okay.
it looks like it's 1.45 OS X.
Okay, cool. All right. Thank you, sir.
Yeah. So did anybody have any burning questions? Did you follow that? Did that make sense?
Excuse me, sir.
Yeah, go ahead, Sarah.
Are you gonna go over the homework?
Yeah, I said I would, so I will. So if you want to stick around, let's do that right now.
Okay, thank
yeah.
you.
I meant to do it earlier, but we ran out of time. So here we go. All right.
Okay.
So let's see. So the homework, back to content. And then I think I have it somewhere else, but I'll just download it again. Homework list. Okay, here it is. Open file. Okay, so here's the first one.
Share your screen, please.
Yeah. Okay, and let me blow this up. All right, so I want you to read chapters 1, 2, and 3 in the data sheet. And just scan through the tables. You don't have to, I know it's hard to read the data sheet. It's a little, it's off-putting, I guess. But go back up here. So chapters 1, device overview. So read through this. Then enhanced mid-range. Just read these things. This kind of helps you a little bit. Look at this diagram. This is the basically the core. We'll go over this in fair detail eventually. But I'll point out a couple of things. So here's the program memory, flash memory. Here's your random access memory, your 1K of 8-bit locations that are random access memory. Here's your 16-level hardware stack, 15 bits. And here's how addresses get put together. Now notice how many address lines are going to the RAM? 12. How many address lines are going to the flash memory? 15. How many address lines come from the BSR register? 5. How many come from indirect registers? well, all 12 actually. How many, and that's 12. How many come from the instruction register? 7. So you get 7 from the instruction register out of the instruction, 5 from the BSR, and that gives you 12. So this multiplexer picks 12 from here or 12 from your indirect register 1 or indirect register 0. So we're not using the indirect registers, but C uses them extensively. And you can use them in assembly language. We're just not trying to complicate things. Here you have 15 bits coming from the file select registers, the indirect registers, going into the program memory. And that's how the file select registers can address RAM or program memory. And they can also address a few other things too. So an instruction's read, all 14 bits get delivered into the instruction register. And then the instruction is decoded, and then it goes through all this other stuff. Here's your arithmetic unit, and here's the W register. So you have a value in the W register, and you can take a value from RAM. The value from RAM then can also, well, comes into the multiplexer, goes into the ALU, and then the output can either go into the W register or back into the RAM register. It can also go, the W register is also fed into the ALU, and the output can either go into the W register or back into RAM. So, and it also affects the status register, and it can use the status register. So this actually shows a lot of stuff. And we'll go through that in a little more detail at some point. But anyway, so read through that, and then finally read through chapter 3. And this is the one where we've been looking at how this is program memory, not data memory, but program memory. So it's 14 bits wide. And this is then data memory, and it's 8 bits wide. And it's every bank is 128 bytes, and they're all laid out here. And just kind of go through and look at this. So you don't have to, I mean, you don't have to painstakingly, all these core registers, they're repeated already all the way up to incom. So all that's the same across all of them. And then so you just have to look at some of these, and that's it. Once you get up here, there aren't any more after bank 8. So just take a look at that and kind of scan through those. You don't have to spend a lot of time reading them. Okay. Then how many bits in the BSR are actually used? You should know that off the top of your head now. 5 bits, right? There's only 31 registers, so you only need 5 bits. List the steps required to change the program counter without using a branch or jump. Well, that's where you preload the latch, and then you write the lower 8 bits in it, and the hardware automatically dumps the latch into the upper 7 bits. And this kind of says it. How many bits in the program counter? Well, how many address bits go to the program memory? 15. So there have to be 15 in the program counter. How many bits in the program counter latch high? The higher order byte of the program counter only has 7 bits because it only has 15 bits. So 7 bits in the latch. When you use a core register, do you have to make sure that the BSR is pointed to the right bank? Somebody tell me the answer to that question.
No, because they're in all the banks.
That's right, you don't. How many general purpose registers are there in the programmer's model? So what is the general purpose register we know about? Let me do this. Yeah, not play yet. So here are the ones I want you to know about. Program counter low, program counter latch high, status, BSR, and W register. what general purpose register do you see in there?
W register.
That's it. That's all there is. One general purpose register. Now, I guess you could argue that you could use the file select registers for general purpose registers too. You kind of can, but you can't really, because you can't use them for any math operation or anything. The only all the data moves have to go through the W register anyway. So you could put information in there and then take it back. I don't know. There's no real way to get it out of there. Well, I guess you could. Yeah, you can use these as storage locations, but they're not really general purpose because they can't be used for math purposes. You can't complement them. You can't rotate them. There's a bunch of stuff you can't do. But kind of. So there's really just one general purpose register, W register. All right. And then what are the 3 status bits and what are they used for? All right, so if we do the status bits, let's see, did we have, I think we did those. So here's the status register. What are the 3 status bits? 0, half carry, carry. The half carry comes out of the first nibble to the higher order nibble. 4 bits to the upper 4 bits. Lower 4 bits to the upper 4 bits. And that's it. Okay. All right. Any other questions?
At what time the lab tomorrow? Is it at 10 a.m.?
I'm sorry, say that again.
The lab is at 10 a.m. tomorrow?
Yeah, we're going to do the lab tomorrow. Yeah,
At 10 a.m. or?
from 10 to 3. We'll run
Oh,
the whole
10.
time. Come in, like I said, you can show up whenever you want between 10 and 3.
Oh, okay.
I mean, don't come in at 2:59 and expect to have an hour. You'll have a minute. But you probably only need about 30 minutes to do it, maybe not even.
Okay. And the homework's due today, yeah?
Yeah,
Homework 1?
yeah, 11:59.
Okay. Thank you.
Just upload it as a PDF or a Word file.
Yeah, I will. Thank you.
Okay. All right, anybody else?
Well, doctor, I actually have a question, but it's kind of personal.
Okay.
So I can hang out for a bit if anyone else has questions.
Okay,
And the lab itself is due in person.
yeah, I'd like you to come to lab and do it tomorrow, yeah. I think, I especially the first lab, I think you'll need a little help. And if you're there, we can help you. If you're at home, we can't. But, if you're really freaked, then try and do it at home. But I'd encourage you to come to lab. That's why we're there.
If we're going in person to lab, do we still need to download the program and get that running on our laptops?
You don't have to. You can use the lab computers. Just bring a jump drive so you can save it.
All right, cool. Thank you.
So you don't want us to turn in anything on Blackboard for the lab?
There should be, let's see, let me pull that up. I think it's there. Here. I think if we go back to course content and then to the lab, I think if we go to the end of the document, oh, actually I have it here. Never mind. Got it here. If you go to the end of the document, there's a little challenge and then you can do some different things. And then there's this lab 1 turn-in form. So you don't have to turn in the whole lab, just this last page. You can fill out your name and then there's a question. Why do we need 2 delays? In this instruction, blah, blah, blah. So answer these questions and then turn that in. But remember, to get credit for the lab, you either have to demo it in person or you have to send Alex a video with your ID card in it showing the lab working. Oh, you didn't see that, did you? My bad. Crap.
No.
And I just.
And all homework assignments are going to be due on Thursdays?
Yeah, so let me, no, not necessarily. I'm not sure. Some of them may very well be due on other days. I try and make them always due on a class day. So there will be either Tuesday or Thursday, but some are on Tuesdays. Okay, so here's the lab guide. If you go all the way to the end, then you can see the last page is this, and that's what you upload that page for your lab turn in. But to get full credit, this only counts like 1 point. All the rest of the credit for your lab is demoing it or doing a video and turning the video into Alex. Okay.
And the lab is due tomorrow?
Yeah. Well, no, it's actually, so the lab is due on Saturday, but if we look at the syllabus, then you can go all the way down here. Let's see.
You're
oh,
not sharing your screen.
sorry, that's the wrong document. If we look at the syllabus, you're good all the way to,
You're not sharing your screen.
sorry, yeah. You're good all the way to the 23rd of November, last day to make up pick labs. After that, you cannot turn them in. That's the last day. But you can turn it, you can, if you want to turn lab 1 in on the 23rd of November, you can do it. I don't recommend that, but you can do it.
Okay.
So there's not, so they're due by Saturday this week, but you can turn them in late without any loss of credit. But I don't recommend it.
Okay.
All right, any other questions?
No, sir. Thank you. Have a good day.
Okay, so if everybody will ring off but Sarah, then she can ask her question.
Thank you. Bye-bye.
Sure thing.
Okay, Professor, can you hear me?
Yeah.
Okay, so I know this class is really heavy on like coding and stuff like that, like programming. And I'm really concerned because I feel like whenever it comes to programming, I'm kind of in the middle. Like I only know so much.
Yeah, so,
And that really
so-
scares
Sorry.
me.
yeah.
Just not to interrupt, but the recording is still going.
Oh, okay, let me, yeah, thank you.
Yikes.